Hello, W&L chemistry students. This is your Unit 2 lesson on accuracy, precision, percent error, and types of error. We'll start with some definitions. What is accuracy? Accuracy is a measure of how close a measurement comes to the actual or true value of whatever is being measured. Now, this is a different definition than precision. Precision is a measure of how close a series of measurements are to one another. So let's think about this for a second. Accuracy is how close a single measurement comes to the actual or true value of whatever is measured, while precision is a measure of how close a series of measurements are to one another. So let me give you a good example of what this means using the idea of a dartboard and a bullseye on a dartboard. Think of the bullseye on the dartboard as being what you want, as being what you're trying to achieve, the true value, the accurate value. You throw a series of 5 darts and you're trying to hit the bullseye. This first dartboard here represents measurements that have low accuracy but high precision. You were aiming for the bullseye here, right in the middle, and you missed by quite a bit all the way over here. So you had low accuracy. On the other hand, every single dart you threw were in the same vicinity of each other. You had very good repeatability. That means you had high precision, even though you did not hit where you wanted to go. So precision is about comparing repeated trials. Now this dartboard is what everybody wants. High accuracy, because you're hitting the bullseye, and high precision, because you have very repeatable measurements that are close to each other. This one is a little bit weird. You think about averaging. So if you were to average all of these throws, they would all sort of average out to being here in this bullseye, getting close to the bullseye. But they have low precision because they are all spread out. So if you were to average all these points, they would come out to being all pretty close to the bullseye. But they have low precision because they're kind of spread out. They're not as repeatable. And this is the worst case scenario. You're aiming at the bullseye and you're not getting anywhere close. So none of these individual throws is very accurate. And you're also not very precise. They're all over the place as opposed to this one that also has low accuracy but is high precision because each one of your darts lands very close to each other. So think about this. Can you have a single measurement that is accurate? Can you do one throw that hits the bullseye? And the answer to that is yes. You can have a single measurement that's accurate. Now review the definition of precision. Can you have a single measurement that is precise? Remember, precision is talking about the repeatability of your measurements. So no, you cannot have a single measurement that is precise because precision is how close a series of measurements are to each other. So a single measurement would not fit that definition. So let's sort of do this in practice by looking at a problem, how we would evaluate measurements as precise and accurate. Read along with me. Sam weighs a mass of known weight of 50 grams on an analytical scale called a balance that he has not calibrated recently. So you have to understand with these analytical scales, these balances where you weigh things, you have to make sure they're calibrated correctly. So each balance comes with a weight that is guaranteed to be that weight. It's been precisely calibrated, so when you put it on your scale, you know that your scale should read exactly 50 grams if it is calibrated correctly. That is your known weight. Well, he's going to see if the scale needs calibration, if it's gotten out of calibration. So he takes the known weight and he puts it on the scale 5 times, and he gets the following readings: 150, 151, 149, 150, and 150. So what can we say about the accuracy and precision of Sam's scale? Well, Sam's scale is pretty precise. It gives him 5 measurements that are very close to each other. They're within a gram or so of each other. 150, 151, 149, 150, and 150 are all very close to each other. So the repeatability is good. His scale is precise. But we do know that the known weight was supposed to be 50, and he's getting weights around 150. Obviously, the scale needs to be calibrated again, and it's not very accurate. Okay, so how do you evaluate accuracy and precision? To evaluate the accuracy of a measurement, the measured value must be compared to a correct value that you have found from a reliable source. To evaluate the precision of a measurement, however, you must compare the values of 2 or more repeated measurements. So you're comparing to see if your measuring device is giving you good reproducibility. Now, a few more definitions. The accepted, or sometimes called theoretical value, is the correct value based on reliable references. We can reliably say, based on lots of reliable references, that the theoretical value for the boiling point of water is 100 degrees Celsius. That's the accepted value that is based on reliable references. Now, the experimental value is a value you measure in the lab, and it may or may not be good depending on your experimental technique. So you might be measuring using lab equipment that's old or not particularly calibrated right, and maybe you get the boiling point of water to be 97 degrees. So that's your experimental value. It is not the accepted value, but it's what you got in the laboratory on that particular day. So when you're doing that, you can calculate the error of your measurement, your experimental measurement, versus what the accepted measurement is, and that's called error. So the difference between the experimental value that you got or the scientists got in the lab and the actual accepted value found in very reliable sources and verified over and over again is called error. And to calculate the error, you essentially take the absolute value, so you don't have to worry about which is bigger or which are smaller. You just take the absolute value of the difference between the two values. So error could be experimental value minus accepted or accepted minus experimental. We usually don't put a negative sign on it or a positive sign. We just say what's the difference. Now we can also calculate something called the percent error. So that's how far off percentage-wise you are from the accepted value. So the formula for that is essentially you're taking your error, your accepted value minus your experimental value, whichever way you want to do that, over the accepted value times 100. So let's do an example. So a scale that needs calibration reads a standard weight of 150 grams as 155 grams. So the standard accepted reliable weight is 150 grams, and what my scale is reading is 155. So what is the scale's error, and what is the scale's percent error? Well, to find error, you just take the absolute value of the accepted minus the experimental. You can do it either way, really, and that's 5 grams. You're off by 5 grams. Now, how do you find the percent error? Well, you take the error and you divide it by the accepted value, so basically 5 divided by 150, and you multiply it times 100. And you'll find that your error on this scale is 3.33%. So your scale is reading off by 3.33%. Now there are 2 types of errors in measurement. One is called random errors, and random errors have an equal probability of being too high or too low. Almost all measurements have some degree of random error. Random error can be minimized with enough trials, and you take then the average of those trials because there are probably just as many readings too high as too low. An example might be fluctuating mass readings on a scale in your room due to air currents in the room. Maybe you've got a very sensitive scale. There's a little bit of air current from the air conditioning system that is blowing on the scale that's causing that last digit to fluctuate a little bit. So fluctuating mass readings on a scale due to air currents are probably going to be equally too high and too low, and that's a random error. Systematic errors tend to either tend towards being too high or too low, just in one direction. Systematic errors do not average out with repeated trials. So systematic errors do not average out with repeated trials. An example would be like what we saw before, a scale that is calibrated incorrectly and always reads too high. Like in our first example, well, it was always off by 100. No matter how many readings we took, that is not going to average out to being the true value. So a systemic error or systematic error is one that tends to be in just one direction. And that is your lesson on accuracy, precision, error, and percent error, and types of error.